The last section in chapter 2, in the derivative chapter, is really starting to get more into the application and kind of a real world context for what a derivative does. So we said that derivatives calculus it's the math of change, and it's the idea that things are changing, and that's what derivatives are representing: a changing slope, a changing velocity when we're dealing with motion. So here's our last piece, which is called a related rate. And what it's going through and talking about is in real life, it is very often common that as one thing changes, one quantity changes, it impacts the change of something else. It's kind of like a chain reaction, basically, or kind of like a snowball effect. So, for example, if actually I'll use a snowball as an example. If I'm pushing a ball of snow down a hill and I'm trying to make a bigger and bigger snowball to make a snowman, over time, my radius of that ball is going to be increasing. We would say that the rate that the radius is changing is increasing. And then that impacts the volume of the snowball. So as the radius increases, it has a direct impact on the rate that the volume increases or that the surface area increases. So again, one thing is changing and it impacts something else. If I was blowing up a balloon and I'm blowing air into the balloon, over time, the radius of that circular spherical balloon is increasing, and that is then changing the volume. So my rate that the volume is changing is increasing, and we would say that those are related rates. We're also going to look at what happens if you take a ladder that's leaning up against the wall and it starts to fall to the ground. And as it falls to a ground, the bottom of it goes away from the wall, so that distance is increasing. The top of the ladder that was leaning up against the wall or the building, it's actually dropping and decreasing in distance because it's crashing to the ground. So again, these are ideas of things that are rates that are directly related to each other. So that's what the long story short, that's the definition of what a related rate is. What you'll notice is with everything I've just talked about, everything is changing with respect to time. So you're going to see a lot of t variables going on. We would even say it's almost like you're doing an implicit differentiation, but everything's in terms of t. So when we do implicit differentiation, we want everything to be in terms of x. So we always write dy dx every time we derive. This time I want to think about what happens in terms of time. So you're going to have a lot of d something dt. So for example, if you're talking about volume changing with respect to time, the way you would write that derivative is dv over dt. That's how the volume is changing over time. If you wanted to talk about the derivative of area, the rate the area was changing, that would be dA over dt. If it's a radius, its derivative dr over dt is how the radius is changing. Circumference, and you could go on and on. Any measurement that you're working with, when it changes, that derivative represents that change in terms of time. So we're going to start this video with just doing a couple basic examples, and then we're going to kind of build our skill set to work with these. So the first example I want to talk about is a ripple in a pond. So when you're talking ripple in a pond, the idea is if you throw, let's say you throw a penny or a rock into the water. This is the lesson where you really get to see my horrific art skills. What will happen is it will create circular ripples that kind of emanate out from wherever that rock or penny or whatever you threw in landed. And over time, the radius of each of those circles is going to increase because you get circle inside a circle and they get bigger and bigger and bigger, and that's going to increase the area. When you're doing these problems, there has to be a formula that connects these quantities. So in this case, connects radius to area. Well, it's a circle, so should know area of a circle is pi r squared. The AP test writers do expect that you know basic area formulas. They will not test your knowledge on like volume formulas. You're not going to have to, from memory, know volume of a cylinder, things like that. But really basic ones like area of a circle or a triangle or a rectangle are things they expect you know. They're going to give you different pieces of information, and you have to figure out what those pieces of information represent. So in this case, it's telling you that the radius of each ripple is increasing at a rate of 1 foot per second. Since that's how the radius is increasing, that is going to represent your dr dt. And it is increasing, so it's positive. And we want to know specifically what the rate of change of area is. So the question is asking, what is dA over dt? So how is the area changing, specifically when the radius hits 4 feet? And there will be a moment that we have to talk about, just like with slope. When I want the slope, it's going to ask for the slope at a particular value, or I want the velocity at a particular value. This is that particular value. You would get a different answer for how the area is changing if I wanted to know what happens when the radius is 2 or 3 or 5. So then the formula that you came up with, it's usually a lot of geometric formulas, you're going to derive that formula in terms of time. So every derivative you take, you're going to put that over dt. So the derivative of a is dA dt. On the right side, you're going to do a power rule, power out front, power one less. Remember, pi is just a number. And then when you take the derivative of r, you're going to include dr dt. So any quantity that is changing, when you take its derivative, you're going to have that d whatever d over dt. So now we're going to put in what we know. We know that my radius, I want to know what's happening when my radius is 4. We also know that my dr dt is 1. So you're going to multiply this up. I would just leave pi in your answer. I would not take the time to multiply out pi. So your answer for dA dt is 8 pi. Now, I mentioned that you never have to convert units, but you should be comfortable using the units they give you. So since this is talking about how an area is changing, this is going to be feet squared per second because it's an area change, so it's units squared. So at the time when my radius gets to 4 feet, that means my area is increasing at a rate of 8 pi feet squared per second. So another pretty simplistic one. I mentioned this a little bit ago about air being blown up into a balloon. So for the sake of this problem, we're going to pretend like this balloon is going into a perfect sphere. I realize life isn't perfect, but we're going to go with it. And as we pump that air into the balloon, it is increasing at a rate of 4.5 cubic inches per minute. Since my unit is cubic inches per minute, that's telling you that it's a volume change. That's your dV dt. So and you think of it as you're blowing air in the balloon, you are changing the volume. Our goal is to figure out the rate of change of the radius. So the goal is to figure out what dr dt is, specifically when the radius gets to 2 inches. So kind of taking that sentence and writing down what needs to happen here. So we do need a formula. So this is a spherical balloon, or as close to it as possible. So volume of a sphere is 4/3 pi r cubed. I will give you this formula. It's probably one that you might know, but you don't have to worry about memorizing it. I'll give it to you. When you take the derivative of v is dv over dt. This side's a power rule, so power out front, the 3's will cancel, power 1 less, and then since you're taking the derivative of r, you need a dr dt. So then you plug in what you know. And again, what I know is that the volume is increasing at 4.5. So I'm going to put that in for dV dt. We want to know what's happening at the moment where the radius gets to 2. So I'm going to put that in for r. And I'm solving for dr dt. So I'm going to divide everything here by, let's see, 2 times 2 is 4 times 4. I'm going to divide everything by 16 pi. Be careful if you're putting this into a calculator. When you type this in, you are going to have to hit divided by parentheses 16 pi, or else it won't divide by both. Now, as far as decimal answers, we really have not worked with decimals at all to this point, so let me kind of go through the standard for you. The standard for any type of decimal when you're trying to figure out rounding, truncating, is you always need to go 3 place accuracy. So for this one, it would be 0.089, or you could say 0.090. You are allowed to either round if it rounds up, or truncate. Truncate literally means just write the first 3 numbers and chop it off. The AP is so focused on those 3 decimals, it does not even matter if you put something totally wrong after those 3 decimals. So if you put 0.089 and then you just started putting like the numbers in your phone number or your lucky number, they don't care. They only grade up to the first 3 digits. So as long as you have that or the rounded version, you are correct. Now my unit, since this is a radius change, is going to be inches per minute because that's how my radius is changing, specifically when my radius gets to be 2 inches. So that's a very basic introduction. We're going to go through more. I'll make more videos, but I wanted to kind of start with the basics to make sure you're comfortable.